like always, give me a few seconds to get set up. Oh, here. This should work. Is this working? I'm not sure it's connected. It is connected. Perfect. Okay. Here. Oh, we have somebody, Yamar. We're both Kabil, by the way, working from Algeria for the dream of being an AI engineer at Apple. Wish me luck. It's funny because I've met in San Francisco an actual ML engineer that worked at Apple. Yeah, so if you're listening to this, shout out. Thank you for the dinner that you bought me when I was there. Okay, so this is good to go. And I'm pretty sure there must be a better way for me to kind of get this whole thing set up. Okay, wait, so I have to go there. This one is working also, and then the last one is this little guy. Okay. And there we go. By the way, one of the first author of this paper, Yasser, is actually from Algeria. So yeah, we have that covered. Cool, guys. So like today, what is this? A little paper. Now, let me show it to you. It's this one. Here. So it's a Falcon Perception paper. Well, I say paper, but it's like actually it's a collection of 3 paper. So you have the Falcon Perception / OCR. You have the Siglino kind of distillation method that they using for like initializing their weight, and then you have like the PBench here that they're using to kind of test this stuff. So like there's actually 3 paper that are related here. Yeah, and basically the whole idea of this is that instead of having like like the for like a vision dense kind of vision task, instead of having like the encoder-decoder paradigm where you train the encoder and then you like kind of lock it with the decoder, they're trying to break this paradigm and then blend this whole thing into one dense transformer. So it's like 22 to 26 layers here, and basically like the image element is gonna look at every patch will look at every patch, and then the language element that is just like literally next to it will look causally at the tokens, and then you get like this stuff right at the end. And based on this and like a few very light custom head here and an image feature upsampler, you can get like something similar to SAM3, much smaller and actually really performant, especially in some specific like benchmark that they're doing for perception. So like that's kind of what we're gonna look at. We have the chance of having the 2 of the authors here from TI, and we're gonna be able to ask them a whole bunch of questions. Yeah, I've prepared quite a lot, so we'll be able to chat it out. If you have any questions, don't hesitate to just like shoot them in the chat, and I'll try to kind of weave them in as we go through this with my guys. So I'm gonna let them in here. There we go. In, okay. And sorry for the voice. I'm recovering, right? I was a bit sick, but now I'm getting a bit better. Yeah, I'm at like 56% of my brain power. Okay, so this is good, and I have all my questions right here. It's gonna be a fun one. So they're getting there. I like this paper because like it's kind of gigantic, but it's not too daunting. Like all of the I don't know, let's say like all the different sections kind of built upon each other, and they took a lot of time to be able to like walk you through like how they're assessing that this thing is correct. There's a lot of ablation throughout. That's a really good one. Hey, how are you? Can you hear me?
Hi.
Okay, perfect. Cool.
Yes, can you hear me?
Yes, yes, yes. We're just gonna wait for Yasser, and then we should be good to go. Where are you guys located, by the way?
We are in Abu Dhabi.
Okay, it's good. I can hear the delay because like whenever I have a call with someone like that far off, there's usually like a 2-second delay between like what I'm saying and then like the people understanding it. Okay, this is good.
You are in Canada?
Yeah, I'm just south of Montreal in Canada. So for me, it's just noon right now. I think for you it's like kind of evening, right?
Yes, 8 p.m. over here.
Yeah. Oh, and I think yes. I think it's coming, but having some issues. Hey, can you hear me? We can't hear you, but we see you. We're gonna get there, folks. We're gonna get there. By the way, how do you pronounce your name?
My name is Phúc.
Okay.
Yes.
Good. That's perfect.
And you Yassin.
Yassin,
Am I
yes.
saying it correctly?
Yeah.
Okay.
Yeah, that's good. It's good enough. Okay. I think. Oh. Okay, he just left. I think maybe it has to do with his mic or something. Okay, round 2. Can you hear us? I think he dropped again. There must be something that. Oh, can you hear us? Is here? Yeah, we can hear you, but wait, you can hear us, but we can't hear you. Somebody is
Somebody
asking.
say hi to me in the chat.
Yeah, they're saying hi to you on YouTube.
Hello.
Somebody asking, est-ce que tu es d'origine française? I'm from Quebec, actually, and we do speak French over here, so I do have an accent. If this is what you're asking.
Nope, we can't
No.
hear you, Yasser. Did Chrome ask you for permission? Did you give permission?
I think he's gonna jump off and come back. Okay. Maybe you can start with an introduction about your background. I kind of did a bit my research, but like it would be nice for everybody to kind of listen from your point of view, kind of your research background coming to this work.
Yeah, so I did my PhD in computer vision in Ireland from 2019. Actually, me and Yasser belong to the same cohort. So, but yeah, my interest has always been on around like representation learning, especially from computer vision. And back then, self-supervised learning, scaling for both text and vision were like a very big deal back then. And of course, we know like for NLP, the one true objective is just next token prediction.
Yeah.
But for like computer vision, it wasn't really obvious back then. And even now, in some sense, I still say. But there is a lot of research back then. And at first my focus was on contrastive learning, but then I realized like doing research at that level, especially representation learning, proving it in real world, does require a lot of resource, which is not really available to me. And so I kind of pivot a little bit into a niche object subject, which we call, let's say, object-centric representation learning.
Okay.
Which is in contrast to like learning a visual representation of an image. And here we try to learn and decompose from the image the set of representation which corresponding to the object itself, so we can capture the property of the object in the latent representation. So this kind of object-centric representation learning, they were like people hypothesize this would be like the unit for reasoning, visual reasoning. If you follow Jan LeCun, he keep talking like this, like representation vector is the unit, and yeah, algebra will be the logic. So that's what kind of the promise, but the field was still very early back then. We train on synthetic image, and the object are like simple geometric object. Yeah, but then so that's the PhD. The PhD you're allowed to explore on the niche, on your interesting topic, but then end of the PhD, the field move on. Ability, grow, everything focus on LLM, vision, or you also build on top of LLM. So yeah, here we are building a VLM.
Good. This is really cool. And I like one thing I like about this paper is that I could see you guys try to like morph the problem into something that like makes sense in let's say have the similar like LM shape, right? Where like you have like this unit and then you can kind of iterate on. without having too much like biases and bloat. It was really cool, honestly. I really see like this kind of progression from what you were saying to what you guys were able to do. Oh, Yasser, can you hear us? Yes. Can you talk? Do you have a mic working? Not yet. Is it? No, there's no. Yeah, there is an issue with your mic. Because we can't hear you at all. No. Yeah. Wait. There's a question that I think it's for you. What do you think about François Chollet's approach and his kaleidoscope hypothesis? I'm not sure what this is about, the kaleidoscope hypothesis. Do you know?
Yes. No, I know François Chollet and his RAGI benchmark. You're right.
Yeah,
but
but
I'm not really sure what it is. Kaleidoscope.
okay. I think what it's saying is that like, while the world appear overwhelming, it is composed of a small number of core repeating pattern atoms of meaning that are combined in different ways. And I think like that's kind of like the unit that you were talking about, which is like,
Yes.
if you're, I mean, in language we see that like very clearly, like you can like kind of have just by doing like next token prediction, you're able to kind of learn this meaning. But I think you're trying to get to the same thing for in the vision domain.
Yes, I think it's on board to the like the same
And-
thing. Like I think as Plato said, you're trying to carve the nature at its joint, trying to factor out all the complex reality into its
Yeah.
independent component, and we compose from there.
Yeah, exactly. And then you just kind of feed the model with high quality data and you let it learn, right? Like that's kind of the dream. There's somebody on Twitter that says, I love Falcon Perception model. It's a great model. So can I sing this? I think it's for you. And how close do you think we are from that? Like to find this unit for vision?
I think we are. I think maybe we already there. The unity on there, it's just not interpretable for some reason.
Yeah.
But like maybe while waiting for Yasser, I can have a story about Distillation. So like I could mention to you about during my PhD about this object-centric representation learning. But then around the end of the PhD,
can you hear me now?
Okay, cool.
Now we can hear you. Yeah.
Yes.
I just connected from my phone. I don't know what's wrong with the laptop though.
It works. It doesn't matter. Thanks for being here.
Yeah, I'm connecting from my I just downloaded the app, and that's it. Sorry about that. I'm sorry.
You can continue, and then Yasa, you can maybe introduce yourself afterward.
Sure, yes, but like I was saying, like for the vision encoder back then, there is a paper about register token.
Okay.
Where instead of in the vision encoder you only have one token for each patch. Now they are appending a few extra token which they call the register. And so the purpose is just for the model to put any unused attention or any extra information, global information into the register token, and doesn't disturb the representation of the patches, so that they can keep a very good like spatial feature in the token patch. But then when they look into the register token, the token actually capture semantic, high-level semantic and corresponding to individual object, salient object in the scene itself. So So in a sense, giving enough capacity, inductive bias in the current model, we might already have something like that internally in vision encoder.
Right. Cool. That's great. Thanks for this intro. Yasser, maybe you can introduce yourself in your background to the community.
Yes. So my name is Yasser. I am a researcher currently at TII in Abu Dhabi. I have done my PhD in DCU, like Dublin, Ireland. And my main research back in the day was focused on self-supervised methods for images, like how do we learn without having access to labels. And like upon joining TII, I started working on mostly large language models, starting from Falcon 1, 7B, 4TB, and 1ATB like years ago. And then obviously because my background is in computer vision, so with coming up of like visual language models, so I'm currently mostly working on this topic. Yeah.
Cool. Very nice. And you were both at like a Dublin City University at the same time. Did you start to collaborate there, or like only when you guys moved into um, uh, the IIT?
Yeah, not
NTI,
really
sorry.
back then.
Okay.
Yeah.
Okay.
So
Perfect.
Yasser actually come here first, and then yeah,
And then you
he asked me
collaborated.
to join later. Yes.
So Phúc used to sit like besides me in the office in Dublin, and we were we were mostly like doing paper reading together like maybe twice a week. So this
Yeah.
is how it started. Like we were like analyzing papers and what's not, but not really like working on a common project. Although we had a common supervisor.
Cool. And then you decide to bring him in the team later on, right?
Yes.
Good. This is fantastic, guys. Can you explain us like the vision behind like Falcon Perception? Because I think like the philosophy of it is very educative about like why you made certain architectural decision, maybe. So Yasser, maybe you can explain to us like what's the grand idea behind this model?
Yeah. So like essentially, like if you are doing let's say, for example, this specific task like dense grounding or open vocab segmentation slash referring expression segmentation, um, like there are like a lot of models of like, for example, at least SAM or detail architectures, which do similar stuff. But for us, we are like mostly like kind of exploring like a different like scaling path, driven by a driven with a different like end goal. So if the end goal is simply to do, I would say, simple nouns for like open vocab segmentation, like segment this car, segment this headphone, this bottle, and what's not, I think like detail architectures might be actually good enough. But for us, like the long-term goal was and is to kind of build this what you call like a perception engine, that either a larger model can call or people can interact with, like in a VQA mode. And this model, it has obviously to do like the current like task, which is like open vocab segmentation, so or stuff like this, but also captioning, or what you call like grounded captioning. This image has this person, but it has to know where exactly this person is. We need to have a good what you call like OCR as an attribute, which is like our level 2 in PBench, which is like identifying things using like what's written on top of them. Also like spatial constraints, like this person on the left, this person on the right, behind, and what's not. But also we care about dance scenes, which is like, let's say when we have like a scene with 200, 300, even like 500 instances of the same object. So this is the second, I would say, requirements. The third one would be we want this model to act in an agentic way, which means given an image, it has to be like zoom in, crop,
Right.
apply some operation if needed to give the answer. But also we want this model to have like to be able to know the limits of perception. say if something is unclear in the image and what's not, like some text is blurry, it has to tell the like the user or the model coordinate like something is like unclear. Can you take another picture or something?
Right.
So that was like the design we wanted to have in this model, right? And once we committed to these goals, which means like for the first two, we need like the model to understand the prompts very well and long tail concepts. And to do this, like for the model to understand like the queries and what people ask, people can like like make typos, can ask in a very, I would say, unclear manner. There's a lot of intent behind it. So obviously we need to mix in text data because this is where this kind of knowledge comes in from. If you want like longer tail concepts, like you want to discover more, you need to train on captioning. So because captioning is cheap at large scale, which means you can know a lot of concepts from captioning, interleave documents, which mean and obviously the current task, which is like open vocab segmentation. And essentially the design behind the model, like because we want all of this, it has to be like single like sequence model. We cannot go for like design all the losses and all the architecture to fit only open vocab segmentation, because this is one of the goals, but not the majority of the goals. Um, so this is why we have done like autoregressive in the first place, because NTP gives us like this, I would say, umbrella behind all this kind of stuff. Now, for dense grounding specifically, like architectures like DETR, usually need what we call like multi-scale, because you don't know at which layer the right scale is for every query or every object. So people like do FP and feature pyramid networks. So which means they feed different image representations from different layers to the decoder, right? But we wanted this to kind of emerge as part of the architecture. That's why we do early fusion. Because if you do early fusion, which means like text and images, they have access to each other all along the way. Which means for a certain query, the model can pick like the suitable layer in a learned manner. Like this is part of the objective we minimize. So this is why we do like early fusion. And one of the reasons also is why we wanted this kind of, I would say, simple interface in an autoregressive way is because we want also to attach ourselves to what people are doing in LLMs. Because in LLMs, obviously, like you have like a lot of scaling laws, a lot of tricks on how to do like long context, sampling, like RLM post training. So essentially, like, by doing but like Falcon Perception V1, we can like already like borrow a lot of tricks
Yeah.
from the LLM community for free. So I would say Falcon Perception V1, the current version, is the first step. Is like step number one. Today it does like open vocab and referring expression segmentation, but the point is we wanted to lock this architecture first, and then we can add capabilities on top of it without like, kind of redesigning the system. So that was essentially the goal, like behind the choices you see in the architecture.
Yeah, kind of like I'd say it like having like this first, I don't know, like the decoder version of it, right? For language, where it was, if you look back right now, like it was very naive, right? But just scaling it led to great things, and then like you can tweak the internal whenever you want to have more capability, and then you rescale it, and then you rescale it again, and you have these waves that led to more capability. The one thing that I'm trying to like understand, why do you think? What's the intuition behind like this being something that can be called by another language model or something like that, versus it being literally part of like a bigger model? What's the intuition here?
Like you mean to say why this has to be a sub agent as compared to like itself having doing the entire stack of capabilities?
Yeah, exactly. Because like you're still doing language in this. Like I
Yep.
understand. Like it says 600 million parameters. Of course, it won't be able to do all this stuff. But do you think that like this paradigm, if you were to let's say scale it to the size of the stuff that we have right now, will end up overtaking this, or like you think it's still going to be something fundamentally different, and that would be like its own core unit?
To be honest, I don't really have the answer to this question now. This is what we are doing currently, what we are exploring. I would say, yeah, essentially the question is, do we need to take like this large orchestrator or large like VLM that has kind of better knowledge, that can reason over like tools and what's not, as compared to like using Falcon Perception, let's say V1 as a like just to do ground. And so this kind of division of labor is not fully settled in my opinion. And I would say maybe two plausible scenarios here. So like the first scenario is this perception engine stays like basic at simple nouns and what's not, but perfect. The current models, us, SAM3, they're good enough, but they're not nearly perfect. For example, on our benchmarks, we are 68 in terms of F1. SAM3 is 62. But like for it like to be like, I would say deployable, usable by bigger models, it has to be like more than 95. Like essentially we have to treat like this basic perception as we are treating, let's say, GSM 8K now in math. It used to be a hard benchmark a few years ago. Now each and every model scores like almost 100% there. So this is the first scenario where these models, like, they do the primitives, simple nouns, they can track, they can do OCR, but the orchestrator does the high level intelligence, like the planning, deciding what to ask next, and does like the reasoning to manipulate the outputs. So this is the first scenario. The second scenario is the perception engine, what we are having now, it like expands a bit. We still like beyond like simple segmentation, but not do like does not expand to do math like benchmarks like MMMU or Math Vista like geometry, but it learns like what you call like grounded captioning, grounded VQA, where it can answer in evidence based manner, like based on real measurements, based on like the segmentation mask or the pointing or whatever. I would say it can be like a VLM but for spatial intelligence. So this is like the two scenarios I see. In both scenarios, like one thing I'm confident like in both is that even perception, like it has to be agentic on its own over images, which means given an image, it has to be able to do like zooming, cropping, do some operations, verifying and what's not, because it has to be robust. The current like models, we just like give the answer. There is no thinking behind it. We just give the answer directly, which means it's more like prone to make some mistakes. So in my opinion, this kind of division is not clear. For example, like the demo maybe you have seen on Twitter, like with Gemma 4 and Falcon Perception, where like we act in an agentic way to essentially, like the question is which bird is flying the highest. That's another, yeah. For example, like any of these demos. So like
Yeah.
this is where this boundary comes up, right? Because essentially to solve this question, like for now, like we need to segment the bird, compute like simple like geometry proxies, and then give the answer. But the real open question is, do we actually need this many kind of explicit like back and forth calls between the orchestrator and the perception engine? Is it compute efficient, right? Or can a small fast perception engine actually can learn to reason over its like latent segmentation tokens to do this like internally, like to compare and what's not, to answer these simple questions? So the boundary might be like possible by like essentially how much grounded reasoning we can fit in these models. So essentially, this is essentially what we are doing now, and we're exploring these questions. We'll see like up to what point we can push, and once we can't push anymore, which means this is like the boundary between these models and the orchestrators.
Cool. I like it. It's a very pragmatic answer here. This is pretty cool. Fab, what's your take on this reality?
No, my take is completely aligned. And I think you mentioned an earlier point about what if these big frontier models they would just be, what they just be as good as a smaller model like this. And I think, I mean, they can, but from the evidence we see at the moment, the vision is kind of mad, and they are prone to hallucination.
Right.
We can have like a argument hypothesis about maybe they are not because they are late fusion, and maybe early fusion can have an advantage. Maybe they can just don't have as good data, or maybe they just not focusing on these kind of tasks at the moment. So,
Right.
so maybe the opportunity is still there for us to provide something that's very good for the frontier model to even bother improving the model. Why they
Yeah.
can just corner something. Yeah.
Yeah.
So
yeah,
that is
yeah.
kind of the best we are taking here.
I think like I think there was a paper you shared, yes, about like the fact that if you just remove like the text information, most of these like kind of frontier models just collapse, and like they're not really like doing much. Maybe like the language biases that they have is way too much. And when you look at the architecture that you guys like did for the early fusion stuff, um, it is really different than like what a big language model will do. Like you can see like the two kind of encoder decoder type of stuff like being put close together, but still it's fundamentally different than what they are doing.
I think, to be honest, like this is like, we're gonna be like a bit of like speculation in here. So if like I think it all comes down to the focus, right? In the sense that, like, let's say you're OpenAI or you're like Anthropic, and you want to build models. Like there are two axes. Like this is like the task, like how economically important is the task. But the second axis, which is very important, is how, like, is this task actually, does it give you access to the final user, or you have to be part of a system to serve the final
Right.
user? For example, the tasks we are talking about in here, like grounded reasoning and what's not. This is, let's say, most of the applications, right? Let's say you are at a pharmacy. I'm gonna just give an example, right? At a pharmacy, and you want to do like assistance of like counting and what's not. So this forces these people, like these companies, to not be the final system, but work with other companies and other people to help them improve their systems, which is, in my opinion, not what these companies want after, because they wanted to go so fast. They wanted to like to grow faster to the point where they went for coding and this kind of like
Yeah.
immediate impact from an economical perspective, but also they have a lot of degrees of freedom because the system is controlled. Now, for like for what we are talking about, like all like the like segmentation and what's not, um, I think it's gonna be there for robotics and what's not, like, or
Mm.
like OpenAI, for example, they published a paper recently called GDP Val, where they actually start like talking about like going for economically like viable, I would say, use cases. And then the question will be there here, because this model also they are agentic now. Will they try to build this kind of capabilities as part of the big model, which might require some changes or to the architecture, like you need to add segmentation? I'm not sure. I'm just speculating in here. Or they're just gonna go there and build a sub agent which is like specific for perception, that is
Yeah.
fast, reliable, and it can accept changes to the architecture. I'm leaning towards the second option. So this is what we are trying to achieve in like midterm. So let's see.
Yeah. Yeah. Makes more a lot of sense, and a very pragmatic take. Again, I like how you guys thinking about this. Um, it would be really cool if you guys could present like the paper. I don't know if you had a slide prepared or you have a noted paper. How do you want to go about like presenting the architecture?
I can't share here. Fook, I have like few slides in for the demo. I'm gonna send you the link, and we can just do it over the paper as well.
Cool. That would be nice.
For the demo.
We
Can
have a
I share
question
my
here.
screen?
I think so. I think you can
Or
share your screen. We have a question on Twitter. It says, What's the limit of object you can track with Falcon Perception? I think there he's speaking about like the amount of dense mask you can have at one shot. Didn't you guys went to 600 at some point?
Yeah.
Okay, so that's
You
a lot
mean
of
like how like how many objects we can do?
Yeah.
Yeah. Essentially, like, I mean, this is like, if we go to the differences between the architecture we have and SAM3, DETR, I mean, in general, DETR, they have like, fixed number of object queries, right? Like, for example, SAM3 has 200. Means the best you can do per prediction is 200. But for us, like, since it's autoregressive, we can do like as many as our DRSS allows. So for now, we are
Right.
doing, we can do like, that.
Cool.
I still need permission.
To
No,
from me or from I give it.
No, for Yasser. Sorry.
Okay.
Okay, maybe I can share the paper first. Yasser, you want to talk? Falcon Perception.
Okay, we are there.
So, you want to talk, Yasser, or?
Oh, go ahead.
Okay, so maybe let's just quickly go over the architecture. So here, as you said, we have only a single transformer where we where we patchify the image, flatten it, and prepend it at the context, followed by the text and the task token. A little bit different from normal LLM is for the prefix image, we let the attention mask to attend jointly bidirectional for both for on the image part, and then this will be follow the following token will still have a causal mask like a normal LLM. And this kind of approach is, I think, first proposed by Gemma. They call it the prefix LLM mass attention, and so first we have an image, and then we have a few text prompt, for example, detect cat, and then the model will condition on the image and the prompt to predict the next token. Here we will, for each instant, we will only predict 3 tokens, which we call the perception, the chain of perception. First is the coord token, then the side, and then the final segmentation. So the coord token will be decoded into 2 values, x and y, which corresponding to the center of the instant. And then the actual numerical value will be re-encoded into the hidden state vector by passing the normal token embedding at the start of the next at the start of the transformer, and it will predict the next token corresponding to the side, but we will actually decode the final hidden representation to the height and width. So together we will have the center and the height and width to localize in a bounding box, and then the model will the final token for the chain of perception token. We still take from the token embedding, but it will condition on the previous image, prompt, and the localization of the bounding box here, and finally we will take this segmentation token to decode into the 5-grain high resolution mask. And to be able to do that, we know one thing for sure we need is a good image feature. So as you can see here, after the transformer, we take out the token corresponding to the image. We pass it to a frozen image feature upsampler. Here we use the AnyUp to get a high resolution image feature. Here is a PCA visualization, for example, of the input image, and you see we have a very good PCA visualization. So that it means like the image feature after the transformer still contain very high and 5-grain, still have a very like high spatial coherence in it. So this spatial coherent image feature allows us to easily create this high resolution feature map by simply a dot product between the segmentation token and this image feature map. And for different masks, we will decode to different chain of perception coord size set, and we will use different segmentation vector dot with the same high resolution image feature to produce the corresponding instant mask. So here, like the main point is that the LLM will handle the localization and the feature of the segmentation token, and everything is done in the LLM framework, autoregressive. So everything is conditioned on each other. So the size of the B box is conditioned on the where is the center of the B box, and the mask is conditioned on the actual B box, and later instant, for example, of a different card, is conditioned on like which other card has been predicted before. And so one single transformer
true. Yeah.
We will handle on the let's say on the difficult aspect, and we have different lightweight head to let's say like inject extra inductive bias into our model. For example, for this reason, we can have an LLM that can do segmentation mask in high resolution, but very quickly, instead of having to predict 100 or 1,000 of polygon token, for example. So that's essentially the idea behind our design of the architecture. Let one transformer handle both the complex part about understanding image, query, and conditional prediction, and just have lightweight head to inject the extra inductive bias we want the model to have about like understanding be able to understand and encode the location effectively, or be able to decode high quality mask efficiently.
Yeah. And from this structure, like it's very clear that like the like image kind of embedding are just computed once, and then like you get like the upsampled element that you need to like do the masking, right?
Yeah.
But then you have your chain of like a chain of perception. From the paper, I've seen that you use like the raster ordering to decide like which mask you're gonna go first, right? And I've seen the plot where like there's better performance for this. But do you see a degradation in performance on like the I think it's top to bottom, left to right, like on the one like at the end completely, like once like he has his condition on everything, right? Like not that on the average, but like it's just the last one, right? Because you're far further off in in the context. Have you run some experiment here on like on these individualized mask errors?
You want to talk on that, Yasser?
So the question was like, why, like, how did you end up doing raster, right?
Well, I know why you're doing raster because it's like it's better, right, than render,
But like,
right? Of course,
yeah.
and like the size. But what I'm asking is like because in this specific scenario, when you're using raster, like I think it's like the bottom right will be always the last one that will be detected, right? So if this is the case, like, do you see? Is there any potential degradation of like these ones compared like to the fresh top left that you have to detect? Because they will like basically at this point in time, the model will just have to do like a simple task, and it's conditioned like on like the image and like some of the stuff that you put there. But as you go further on, you have much more that it is conditioning upon. Is something like this happening, or is actually like the opposite, where it's actually better?
So yeah, first, like, why why we ended up in Rust, because they're related actually. So when we started this project, like when we started doing like, the trainings and like setting up the parameters and the choices, at least myself and Fook, we were convinced that we will never do raster order, like, because like
And
it's
here
kind
we
of
are.
like it's like it's kind of like it's not desirable, and the reason is because we wanted to go for like random, because if you do random, you kind of enable kind of in context refinement. So the first object is kind of refined on the second object and what's not. And this is like that was like until 80% of the trainings. We were like always training like with random and what's not. And then one of the days, actually Fook was doing the analysis of like, you take the first coord token and you see like the probabilities of the coord head over the next ones. And we see that actually the model is not doing a lot of refinement. The model is too confident that I'm gonna do this object, I'm gonna go to the next object and what's not. There is no like it's not probabilistic. It's not like 30% this or like
Right.
70% the other. And then we say, okay, so we kind of know why. This is maybe some mistake we have done in the architecture, like the way we like kind of factorize the bins in the coord head, but it was too late because it was designed and implemented and what's not. And that's why we went for raster. So we
Right.
went for raster because of our design of the coord head. And because the model actually was not doing a lot of refinement. And so like the quality of like top left is pretty much the same as bottom right.
Right. Okay.
So yeah.
Yeah, I want to expand on this a little bit about the difference between psi and raster, because our particular choice of decomposing an instant prediction into coord, which is the center, and then the psi, and then the set, which is the final mask. So, like for example, if we do the ordering as size, when the model look at the image, the first instant it had to predict need to be the instant with like the
Yeah.
has a larger size, but the psi token is only predicted after the coord token is predicted. Why, if we do raster, the ordering of the raster order can be determined just by the coord token, the center of the the instant. So by because we make the architecture always predict the center first, and raster order align with the center. So the model can learn the raster order just by the first instant, by the first token of the three tokens. So I think that's our hypothesis of why for our particular model this time the raster order were bringing such a huge improvement.
Yeah. That makes a lot of sense. I had also another question about just like the general idea of the architecture. If you can go back to the main image, like it really looked like you took like the kind of encoder-decoder kind of separated architecture, right? But then you just like jammed it into like the same kind of model. Like, what was the rationale to? I know that like you guys look at polygemma and like it was working there. But what was the rationale for like having it like this and in this particular configuration with like the head helping in this flow? Like, how did you go from like literally nothing to this figure?
Maybe talk about our head. For example, like the center and the side encoder-decoder, we have to give credit for Muon Dream because we studied this specialized head. We were inspired by Muon Dream too. Even so, I think they predict 2 coord token for X and Y, and then 1 side token for H and W. In our case, we were inspired by it, but we just like clean it up a little bit, and we decide just 1 coord for X, Y, 1 side for H and W, and we use the Fourier-feature as for to design the encoder so that the model can have the best chance to look at the actual to encode the actual numerical value, and and for the segmentation head, because we really don't like the idea of predicting a huge amount of token just to form a polygon. So we know we need a design that can generate on the mask at once. And for that, we know we would need very good image feature and high resolution as well. So high resolution, we impact the finer detail, but we know we need an image feature that's like has very good spatial coherence and spatial feature. So that's why we equip our in the attention layer the full mask over the image token, because so that the representation between each token can attend and refine each other. And we can do this because for image token during training we do not put a loss on it, so there is no breakup causality, etc. Basically. So yeah, so that's what the idea behind the architecture.
And we tried also actually like maybe for like maybe a month and a half or even 2 months, we tried actually being causal, because we know like doing like full followed by causal is not I would say not integration friendly, because you have issues now with VLM and Llama CPP and all these kind of frameworks. So we tried for a while like doing causal like AnyV2 from like there's a paper from Apple called AnyV2 in which they do a kind of next patch prediction. So each patch predicts the next one. And we had like this loss where we were doing like like next patch prediction and what's not. But because we do segmentation, we had kind of leakage in the attention. So it was learning, but not that good. Right. It was just okay. And then we went like up the prefix LM where we randomly sample like a value between 0 and 1, and then we do like fully causal, so like full mask up until then, and then we continue with causal and we apply the image loss only over the remaining part of the mask. And the reason we do this because we wanted to be able to switch in the mask any way we want, like in like either direction we can go, like because we do hybrid over the same image, like at pre-training, which means at SFT at inference we can either go fully like block for image or we can go fully code. We tried these kind of things, but it was adding a lot of complexity to training, and it was like making the training unstable. So at the end of the day, like because we start from a distilled model, like for like these models, they're like actually using like full mask. So we had to adapt. We had to stick to this kind of mask for images. So I think now we are trying to, for this current model, like go causal and fine tune, because ideally it should be causal actually, because it's like integration friendly. But let's see where we go from here.
Right. That makes a whole lot of sense. And then I had a question about the chain of perception, right? Because you have the coordinate size, and then like segmentation. I think you tried just the segmentation, right? But it was way too heavy. Can you talk us about that? Because I think like the actual funnel is just like to make the problem, the segmentation kind of token that it has to do be much simpler, so that like you can simplify a bit the architecture for this. Was this the reasoning that you were going for here?
Yeah, essentially like at the beginning we did not have this like chain of perception. We had what you call like the object token, one token. We wanted like every instance in the image to have like one specific token called the object
Right.
token, and to do the dot product and what's not. And early on in the training, when we started with this idea, what happened is, like, because you don't have any kind of encoding of this, like the masks, the instance masks. Like what happens is when you train, the model starts predicting like semantic masks instead of like instance masks for the entire text. So person does what, like for the first person and the last person, they all share the same semantic mask, which is like
Right.
over all the people in the image. So when this happened, so then we have two options here. The first option is we get like a mask encoder. The second option is we condition based on coord and size, based on the B box. The reason we went for the second option is obviously it's lighter, because you have like just like two values instead of like encoding the entire mask. But also we wanted to give, like, once we train this model, we can easily turn off the segmentation and have it as a detection model, which is much faster, of course.
Sure.
So we can do like coord size seg, and then simply do not decode the seg token, keep coord and size, and then become the detection model, a faster detection model. So this is how we ended up like with the chain of perception.
Oh, this is pretty cool. And also just generally like, because there's also like a whole bunch of decision in there. Like there's like the upsampler that you decide to put over here. There's like the native resolution, right, for the stuff. There's the 3D rope that you decide. How did you go about from like the basis that you had at the start to select which element to try and add into the mix?
To be honest, a lot of the choice here, quite vibe based.
It's always like this. Every time I ask this question, people are saying like, "Yeah,
Yes,
we thought this was like looked better into the system." I love it.
yes,
Hook has a
but
saying in the team which says, you start with the most um, correct place and debug from there. So essentially, like yeah, it's like I would say most of the so we had like when we were starting doing this, we wanted to be kind of following what's happening, because it's actually so much aligned with LLMs. So
Yeah.
we follow the current literature, we follow the best practices, and obviously like reason about like our targets, what do we want in the architecture, and use it there. So, for example, like the 3D rope and what's not, this actually was part of the distillation project, in which it actually proved to be helpful, because it gave us the chance to essentially, for distillation, maybe I'm not sure, maybe you're gonna talk about it later, but for distillation, like you take people like Radio, like some other works, they do it like stage wise, right? They
Yeah.
do like start with a small resolution, 256, they go to 384, and they keep like increasing the resolution. That was not the way we have done distillation. We have done it like with mixing all the resolutions from scratch, because we believe that a pure, I would say, training recipe always wins. But if you do it like this, which means you're gonna have no issues with like with with like interpolation of like the image, like the image representation from small to big and what's not. So in distillation, when we tried like 3D rope and this kind of techniques, what ended up happening is we train, let's say, at 1024 max resolution, and then at test time we blow up the image resolutions to 2K or 3K, and we see that the PCAs they get better with a higher resolution,
Right.
which is something you wouldn't get with 1D rope. So that was the reason behind 3D rope. So essentially, like it was like one of the most, I would say, kind of state of the art way of doing positional encodings if you want to do like images, like mix up images and at a native resolution. But so this kind of, I would say, this kind of like reasoning behind how do we choose things in the architecture, it has also a downside, because sometimes we try things. For example, our activation, we went from Swiggle to Relu Square. The reason we went for Relu Square because like in the nano GP, like in Andro Karpati code base, people like praise it a lot. So we train with it because of the premise, it's kind of faster and what's not. But we ended up having like large activations in the model, which made it hard for quantization and what's not. So yeah, so I would say the lesson here is like it's good to always try to go for the latest techniques, try to implement them, improve them, and what's not. But we have to be very careful when it comes to kind of very well established, I would say, techniques that are already there, and changing them that might have some side effect, I would say.
Yeah, and there's so many moving parts also, like in this thing. Like if you switch one thing, then maybe something else start to like not function properly. Have you had to do any gymnastic with Muon whatsoever to like make it work? Because like you had to switch. I think you switched from AtomW to Muon, and it was kind of better and more stable. But I know that like every time folks need to like, especially in language, like they use it, they have to do a whole bunch of work to kind of like stabilize, right? Clip it or whatever. But then they get a very smooth kind of loss curve. Did you have to do anything to make it work here, or?
Yes, so for Muon, we try a lot of things, a lot of different implementation, but we end up using the Dion package from Microsoft. That were, but we still use the Muon optimizer from that Dion package.
Okay, right.
And they were a lot of blowing up, more than not converging, lost blow up, etc. But then we settle on the Kimi Moonlight scaling rule for Muon, which very conveniently allow you to reuse the same learning rate of AtomW.
Right.
So the moment we switch to that scaling rule of Moondream, reuse the same learning rate, everything smooth. We immediately
Nice.
see like a big improvement over the loss.
I love this.
Because for us, like to be honest, like the usage of Muon was almost surprising in terms of performance, because
Right.
like we have these specialized heads and we have like multiple loss functions, like for segmentation and for next token prediction. Essentially, like the performance was like day and night.
Oh,
It
yeah.
was not close, was not even close between Muon and Adam W. So it was kind of surprising, to be honest.
I saw the graph. Like the gap is really there, um, and in the paper it looked like you just plug it in and it worked. But it seems like it was kind of a bit the case for this. I have a whole bunch of questions about like the distillation, but maybe you can continue. I think you had the slide that you wanted to show. So if you want to go through this, and then I can ask my question. We also have like a bunch of questions from the community, but yeah, we can go through the slide first.
Okay. Do you see the slide, or do you still see the image, the paper?
We still see the paper, yeah.
Okay, share this tab instead. Okay.
Okay, perfect. We see the slides, yeah.
So the
Okay.
slides, I just wanted to put a few examples in which. So maybe before we jump into the slides, maybe you should like define PBench if you want.
Yeah,
Yes, you
good idea. Yeah.
yeah.
Okay.
So essentially, like if you go back to the paper book, yeah, for PBench. So when we started like doing this, like obviously there are like simple nouns, right? Like you can just you can stop there. The table, yeah, the table. Essentially, like if you are doing like open vocab segmentation or referring expression segmentation, so essentially you're asking a question. You are asking to identify either like a noun, a concept in the image, and for this, like users like have many degrees of freedom. Like they can ask like varying stuff. They can go from simple like nouns, like car, phone, whatever, as well as more, I would say, compositional, uh, compositional, I would say, concepts. So we wanted to, before we start like training the model and even like benchmarking and seeing the current performance of the models like back in the day before SAM 3, I'm talking Moon, Dream, and Quan and Gemini. We wanted to essentially understand from a fine-grained perspective where these models work and where they don't when it comes to this like task. So starting from simple words like car, phone, laptop. So this is like what you call simple nouns, and then users can actually add attributes to these nouns. Can give an adjective, like let's say a red car, like a blue phone. Like color can be an adjective. Size, the larger phone, smaller one. It could be like the adjective or the attribute, like can be anything. Like user simply can identify whatever they want and ask the model. And our models have to be robust into like answering such stuff. If new out this kind of stuff, like door open, door close, like the functional behind the query. But also then we realized that actually one of the attributes, which people actually ask a lot, is using OCR as an identifier. You have like shelf or in a supermarket, and people ask Coke or Pepsi. So they're not interested in all the cans; they're interested only in the Pepsi one, which means the model has to identify the cans, read which ones are Pepsi or Coke, and just segment those. And then we have level 3, which is when people start like giving the sense of direction to the model, like left, right, like the model has to be like spatially aware of what's going on. And the fourth level we were interested in is what you call like relationship actions. When a human being is actually doing something, which means it involves like a relation between two kind of entities in the image, and one of them is operating using the other. Like where the model like this is not a video, we are talking about images now. The model like just like has to understand the concept, understand the concept, see like based on the context whether which person is talking among the people. So these are the 4 levels. There are other levels that we identified require like a bit more reasoning. For example, level 5 would be you take there's like some dirt on the floor. You take a picture and say segment like the area to be cleaned. So the model has to understand that this is the area, this is the dirt, and this is like what should be cleaned. But those not like actually done for the sake of this project. And then we start doing like evaluating models and see like where model work and where model do not work, and we see like a clear like scaling between level 0 to level 4, where level 0 is you have like a certain performance and starts going down like among the levels because complexity grows up. So essentially like this is how we built our benchmark, and this is how we built our capabilities. That's what this model does. And just as a side note, we were surprised actually by the way that just by doing this, we realize that most models, including ours for now, they struggle a lot with level 2, which is reading in a while.
Yeah.
Like we see like huge drops like for most models for some reason. And when we started doing this, we were thinking, oh, like identifying the sense of like left, right, bottom, and this kind of stuff might be harder than just reading text. But it turns out the opposite.
No.
Actually, reading text in images is like much harder as compared to identifying the sense of orientation, because text is high like high frequency, like noisy, like
Yeah.
it could have like multiple things like and whatever.
Yeah.
And these drove our data generation, annotation, and what's not. So maybe if you can show the slides there, I'm gonna
But
go like.
this part is very interesting. At level 2 is hard because when I was reading the paper, like I know that you guys like did a very smart like distill of Dino V3 and then Siglip 2 in order to get like Siglino, and then like this was the weight initialization for the model. Um, but then you didn't do that for the Falcon OCR, right? Do you think that this has to do with it, like in some shape or form, that like this very high bias at the start toward like these more I don't know like natural kind of shape versus like the language thing, which is like much different, has something to do? Like I don't know, like did you try to just randomly initializing it and see if actually level 2 will be better at the expense of like maybe the other levels?
Yeah. So like actually the reason we have done distillation is precisely to improve level 2,
Okay.
because assumption was if you have Siglip, which is trained on captioning, trained a lot of data, so it should actually start learning uh, to read things in the wild, because
True.
like this is how captions are. But as you mentioned, OCR was trained from scratch. But these are like, it turns out actually like reading in documents, like where the background is kind of like you don't have the noise coming out from the background,
Yeah.
or even reading in the real world, but like a blobs of text. You have in the real world, but you have like some part of the text written and you read it. Is a completely different task as compared to reading on objects, where you have like the background, you have the color of the object and what's not. So it turns out this specific part of OCR is the hardest one as compared to the other part of OCR, which is like
Right. Okay.
reading
Okay. Okay.
documents. And
Okay.
level 2 does not do like text, like the blobs of text and what's not. It uses OCR as an identifier on top of objects.
Right.
So like so level 2 is still even hard for our Falcon OCR model, like reading in the
Okay.
wild. So,
So it should be level 5 then. Why you put it level 2? Put it level 5.
because it's an attribute. It's OCR as an attribute.
Yeah.
So that was like we are surprised. Like that was surprising actually for us, for all of us in the team. We were thinking, oh, level 2 is easy. Let's worry about level 3 and 4. And then nope.
These model, huh? This is pretty cool. Before we move on, like, can you just explain like how you guys like made PBench? I know like you have another paper on that, but I really liked how like you were able to a bit like in Sentry where you leverage like other models to kind of go and like bootstrap like the segmentation and stuff and like the labeling, but then you didn't discard those that the model were not able to do, so you still have very hard tasks that are rooted toward humans. I really like this. Like, can you explain it a bit how this whole benchmark was created?
So the benchmark was, so this is what you just mentioned, Yassine, is for the training data. So for the benchmark was so we have
Oh yeah,
we
true.
have like a bunch of images, and it was like annotated and created by the team members from scratch. So we get an image, and then we say we want this image to be in level 0 or level 1 or whatever, and the people like they look at it and they create the query and do the segmentation by the team member. Because early on when we were doing this, like looking now, it looks like even for us it looks like kind of clear. But back in the day, like 6 months ago, it was not clear what this
Right.
benchmark, what these levels are. So we did it like the benchmark was done like inside the team, and then we try to replicate the way the benchmark is. I mean the levels into the training data, which means when we get
Yeah.
the image, we create like level 0, level 1, and whatever. And we know, for example, that like some was not that our V2 Moon Dream is very good at level 0 and 1, but we know also that Moon Dream struggles with level 2.
Right.
So which means Moon Dream was discarded when we annotate for level 2. So it gives this kind of profiling that served as a signal like to like direct the data annotation. So coming back to your question, So for data annotation, what we did is we did this kind of consensus between models. So we take like a lot of data, and we like run like detection because these models are for detection, to be clear. And we do like we do like measure where they do agree upon image and the query. All right. But obviously we cannot train on this data because this is kind of the easy-ish data. So our model will never be better than the models used. But for what they don't agree, there are multiple categories, right? So they cannot agree because the IOU is lower than the threshold, which means model one has a certain box, model two has box on top of it, but it's just a bit larger. This is one option. They can agree on one object, but not the second one. This is another object. This is another option. But this is not what we did for human annotation. For human annotation, we went for cases where it's kind of binary. The two models have literally zero intersection.
Right.
Model
Okay.
A is saying this object or this query is here. Model B is saying is there, which means one of them is completely wrong or both of them are completely wrong. And by doing so, we are sure that we are kind of patchifying in the knowledge
Yeah.
where these models do not work.
Yeah.
Which means if you train on such data, like by definition, our model has to be better. So this is essentially how it was done, and this was done per level.
Okay, then it makes a lot of sense. Um, uh, how come like this model that you have, Falcon Perception, is so good at like the area where like the other are struggling? Because literally like they we're able to see like these hard tasks also. Um, this is fantastic. So guys, you can continue. Sorry for all the questions. Um,
Yeah.
Great question, Muon. Okay. Uh, maybe Yasser, you want to talk over this? I
Yeah.
can
So
attempt the slide.
I just wanted to show what do we mean actually by levels, and the reason I want to show this is because for people listening, just to give them an idea of how to use Falcon perception, like what it does and this kind of stuff. So I did not do level zero because I think level zero is like is common for everyone, like just like common nouns, like this is obvious. So the image you see in here, the prompt is what we call level one. So you have this kind of candies, and the user can ask, like, we're not interested in all the candies, but we're interested in the white candy coated chocolates. So this was given to our model, and you can see that our model only selects the white ones, like over the masks, right? Not not other colors, and obviously, like people can ask for other colors. So this is level one. We are using attributes to retrieve the objects of interest. The same thing for the second image, which is, you have like a few birds in there, and the user can ask seagull with the yellow beak. So among all of them, this is the one with the yellow beak. So just to illustrate to people, this is exactly what do we mean by by level one. All right. And the slide three is level two. Okay. So for example, you have this image of, I suppose, some shop, and the user can say Tokyo 3 hoodie. So the model has to look for all the hoodies, and just to retrieve the one where Tokyo 3 is written. Same thing for the next image. Um, like this is like like you have a race, and the person can ask the Jaguar Bud Light race car. So this is Jaguar on top of it, Bud Light. So the model has to read to retrieve. This is level two. Obviously, um, these are like, I wouldn't say cherry picked examples, but I had to try four examples to select two in here. So we are still struggling with level two, such that like we are like even on the benchmark we are better than some three and other models, but this is far from being a solved problem.
right.
And we are targeting this for the next iterations. All the other levels, it was like literally first shot. I did not have
Wow.
to even cherry pick. So it was like the
So
first
that
example I
so
tried in the
there's
model.
Yeah, so there's really something about this specific task that is a bit different than others. Um, just like random idea completely. Would it help if the model knew like ahead of time what type of level it has and like inject that biases straight into the model? Because I would assume that like just from the prompt you could kind of figure out like in which kind of cases. So here the Jaguar Bud Light race car, like you would be able to say like yeah I'm level 2 because I will have to read stuff, right? Do you think that this will help in any way the model to kind of like improve without changing too much in the architecture?
Yeah, definitely, yeah, definitely. I think yeah, yeah. I think yeah. If you give like, but like maybe we should also add some like we need a COT there, right? Because the model has to read like a few other stuff and select. Even if we do it
Yeah.
like this. Yeah, yeah, yeah. We'll try. We'll try. We are trying to solve this in different ways. Let's see. let's see. Let's see where do we reach. Like it's
Yeah.
surprising. Like even Moon Dream and other models they struggle with this. Something to it. I don't know why.
To something, yeah.
Um, so then like level 3 is the next example. So this is like you have a building, and the question is like potted plant second from the right. So you have like to go to the right, and the model has to like this is the first, this is the second. So it does it correctly. So
Wow.
this is level 3, like like second person, like left, right, this kind of stuff. Same thing
It's
for
crazy.
the
Like it's absolutely crazy that this is easier than the first one, the one just before. It's crazy that like
yes.
it's able to look at this and like potted plant second from right and then go here right away. Um,
I think just text is high frequency in the wild because the background is literally acting as noise, and the model is not
yeah.
able to essentially read for some reason. Maybe resolution. Maybe we should go to like even higher resolution. I don't know. We'll see. We'll see. Like, how do we solve it? But yeah. But this is essentially what that was the goal behind PBench, because now we know where the model works and where it doesn't, and it like gives us a signal of same thing for slide 6. So that was the image, and we say white car in between two black cars. So there is another white car, but behind it there is a boss, and in front there is a red car. So the model knows that this is the car we are talking about. So yeah, so this is level 3, sense of direction. It has to identify stuff. In level 4 is there's a person playing trumpet. So it, there are 4 people. It identified this one correctly. This is level 4, which means the person is actually doing an activity. So the model has to identify the activity and like identify the correct like person doing whatever. Um, so this is level 4, like person walking as well. On the sidewalk, it missed one on the very far, but like it's fine. It understands like this is the sidewalk. We're not talking about the 2 people like riding the
Yeah.
horse or
Well, I
something.
think you got it. No, like I see the mask
Yeah.
on the very far. Um, you
I
got
So
think,
both.
yeah,
Okay,
we
no, this
still
one.
miss one
Easy
over there.
walking. I'm not sure if he's walking actually. He's waiting for the bus.
yeah, maybe not. Yeah.
You would be an excellent labeler, a PBench annotator.
Yeah.
Yeah.
If you
So
need help, guys, let me know. I will be happy
yeah.
to annotate a bunch of stuff.
So like if you can go to level slide 10, so this is what one thing that why we do like autoregressive, right? And why we do autoregressive while having the chain of perception, because autoregressive obviously gives us the chance to do like as many objects as our model allows or our data set allows. We're not like bounded by, let's say, 200 object queries, and then you can do it in a single shot. We are not also SAM3, for example, you can do it, right? But you have to tile the image. Like you have to tile the image, and then you have to, if you tile, you have to resolve all the issues that come at the borders, like overlap and whatnot. But for us, what was surprising is like the model actually generalizes to do like 200, 300, up like for now we're even able to reach like 600. I would say 600 predictions without tiling. without like doing any like just one shot. It goes like autoregressive. It does them all. You see this like the coin in here, like it does them like most of them. I don't know how many are in here, but like a lot, maybe more than 200. Same thing for the birds. The example like in slide 11, um, like same, like yeah. So this is like the lemon, I suppose. Yeah, on the tree, which is like harder, obviously, like it's occluded and whatnot, but the model still does it. Same for like the image on top. The next image as well was really surprising. Like I
Wow,
think there are like almost
crazy.
300 things in here, and it's a single shot, like autoregressive single shot, and the model is not repeating. Like it's not like it's like goes into this repetition mode where it's like
Yeah, yeah,
collapses on the single thing, which was really surprising to us. So this shows us that we don't know if early fusion really helps here. Maybe it does because the model has access to all the features, but at least what's for sure is chain of perception makes it like efficient because essentially if the model produces 250 tokens, that's sorry 250 objects, for us that's only 750 tokens. Chord size seg, that's it. 750 is very fast to generate as compared to, let's you do like polygons and you have to generate like I don't know like thousands of tokens to do this image.
yeah.
So and obviously autoregressive because we don't have like essentially like bias over how many objects we can produce. So yeah, so I just wanted to show these examples, which reflect the benchmark, and this is essentially what we expect people to use the model for.
Just a caveat, it said in the slide, but I think Yasser have mentioned this is from our reinforcement learning improvement of our
Yeah.
current model, which has not been released yet. Currently, the model is still struggle a little bit, can sometimes collapse on these dense case, but our early RL experiment already showed that the capability in there. We can
Exactly, because
quickly
of the
pick up
pass
with
at K
RL.
thing, right? I think you did pass at 8,
Yes.
and then it was able to kind of like find these, but you need like a few try. So then like with
Yep.
the RL, you're able to kind of like get the pass at K in pass at 1, and then get it
Yep.
there. Yeah, this is
Yep.
so cool, man. So cool. Uh, um, uh, do you think it will help, like, if you had, like, I don't know. I know, like, adding tokens for the stuff um, is dangerous, but in my view, for like level 2, it seems to make sense to have like, hey, where is the object? It's like here, and then you have the bounding box, and then you have, I don't know, like a captioning token or something like that, and then you have the segmentation, so that it knows kind of like the language can be injected in here to kind of modify it. And if it knows early on, like if the model is able to know, am I in level 2 or not, right? It means that they can kind of disable this one if it's not needed, and then you can get like just a normal segmentation behavior, without having like this kind of middle token in the middle. But it seems like uh, the uh, the the problem is maybe too hard when you look at like the whole thing and you have like all of the background affecting. But like, if you're kind of like limiting yourself to like where the bounding box is, maybe it will be a easier task for the model to take. Um,
Yeah. I mean, look, this is what we are doing for V2 actually. Like the
nice.
second version, it is like as I mentioned in the beginning, we wanted to be authentic, we wanted to crop, like
Yeah,
detect things before it does because we want this kind of reliability. We don't
that's
want
it.
essentially to ask a question like for level 2, 3, and 4, and hope for the best. Like we don't know what the model is doing, and we don't want it to be up to our training data, because if like we know it's kind of very hard to do it like for SFT for training. So we need like reinforcement learning because it generalizes better supposedly.
Yeah,
So yeah, we are doing
but
this for VT. Let's hope.
yeah, that was a. I mean, like we can go into like the few questions I had still. The reinforcement learning part um, is kind of very interesting for me, and like the fact that you're able to get these results with like that stuff, it really make me think about like R1 because you're kind of in the same shape before reasoning kind of get arrive, and then you can have like these kind of composition of action in whatever kind of token space that you define, right? In language, like we're just gonna talk, and then like I'm gonna make a plan, and then like it will scaffold myself. It will take more time, but it will be higher quality. But it seems like you have all of the ingredient to be able to do that and have like the token being like generated in order to have a better output. So from the earlier experiment here, like how does the RL work here? Like what type of token is it outputting in order to get like the thing back, and like what's the reward signal here?
Yeah, so like the current reinforcement, it's not like really reasoning what you are doing. It's mostly inspired by there's a work from Lucas Bayer about like using reinforcement learning. Got the name of the paper. Training computer vision with task rewards. So because the way we train with still with cross entropy and what's not, but the way we're measuring performance is using F1, which is might not actually align with the task risk. So for now, what we are doing is we have like you mentioned the cases with like positive 8 and what's not. So we have few rollouts, and we want to make the right ones like more certain. So the algorithm is obviously like GRPO, and the reward function we are using for now is just like F1, and like just like to balance between like recall and precision. And we have like we already have like few findings. The model is much better at like low context and what's not. But for us, like because of the architecture, uh, the obvious question is where to sample. Do we sample in the LM head? Do we sample in the coord head or in the segmentation? So obviously, like throughout our trainings, we realize that there is one loss, which is the coordinate loss, which is actually very indicative of performance. Means what? Means our backbone is the one doing actually most of the work. Like like the first pointing coord, like this object is there, here, and what's not, is actually like the heavy lifting happening there. It's not the fact of the model does not struggle to predict size after coord, and the model actually does not struggle to predict which segmentation token once the B box is correct. Becomes more of a refinement inside the B box. And for this, what we did for now is freeze the size and segmentation, and the LM head and sample only in the coord. This is where we sample. Just like
Okay.
one place where we sample, uh, and the reward being F1, and we see like huge gains in just by this. So we see like the model becomes much more certain now over predictions. We don't. There is one metric that we have called MRR. Internal is not actually, we did not put it in the paper. Maybe we should add it. And MRR simply means mask redundancy rate. You take your data set, you generate, and you see how many, and you do NMS, and you see how many masks were deleted. So we do this for dance, for example, the dance split. We see, for example, like models like Moon Dream is like literally like 40% MRR. They repeat a lot when it goes to dance because it's harder now. Like we have a lot of samples. Same thing for Quen. Our current model is around like 10% of redundancy over like these samples, the ones you see there, like very dense ones. And surprisingly speaking, when we do like after like GRPO, the MRR goes almost to zero. The model stops like repeating at all,
Wow.
and which is surprising. Yeah.
That's kind of crazy. Um, yeah. I had two questions actually. Like, um, if the coordinate element is the hardest, right? Would it help to you think that to give it multiple try in order to kind of like get it right instead of just like one shotting it, especially if like there's many of them, right? And then just like letting it scan the thing multiple time while still being preconditioned by the try that you had in the past. Um, do you think that this could help in any way, or like we will confuse it more because now he has to keep track of like the first shot that he had and like try to correct it, but later on, what's your take on that? I'm literally shooting you all my ideas.
Yeah. Yeah. See, I mean, like, for it like to have multiple tries, we need to be confident that the coord token is being refined. That is in context, right? Because when it's refined, then like few refinement you can get it correct. So, which is not the case for the current model. The current model there is some refinement, but not much, and we will fix this in V2. Like, which is like we know where the issue. The issue is mostly with the core encoder decoder and the way we're factorizing. But yeah, so essentially after like after we have this behavior where it's random, we're not doing raster anymore, and it's being refined, which means there's a lot of in context. The model learns from the context, like where to look first and what's not, and then trials and stuff like makes sense at this stage, I suppose. Maybe Fook,
Because
if you have some.
Yeah, because
Sorry,
then
yes.
like you have like this reasoning shape, because you could like put it into like, yeah, we're just trying stuff, and then you can throw it away and stuff. It will take longer, but then if it is able to do this kind of refinement, then like my guess is that whatever is working with RL will work even better, and then it might be learning to refine on its own, and then it's off to the a similar type of scaling and shape that what we have right now, but just a better take on that.
No, I think this is a great idea. Yes, but like in order to do that, we must have I think it belong to the general trajectory that we are trying to do, which is trying to make the model a bit more agentic. But like I think this idea is like fit perfectly into this framework because the model can predict coarse size set, for example, and if it predict a little bit off, the segmentation will be something very weird, very yucky, very high entropy, and the model can have this segmentation token inside, and then it will see, okay, this coord inside yielding this very bad looking segmentation. So internally, it already know it is wrong as soon as it sample, and then it can condition on that, try again, no, it's wrong, and try again. But yeah, I think this is a great idea. Yeah, it can work, but the model need a bit more capability. It needs the agentic capability.
Yes.
But I think all
Yeah,
the
definitely.
ingredient are there.
Yeah, but like that like if I look at like everything that you guys have, it seems like all of the raw material for like that stuff to happen is like almost there. Yeah, it's very interesting. Maybe we can chat about a bit about the distillation process, because I found that was very interesting, and I know it comes from the AMOE, a paper that like got like then you defined it as Siglino, but I thought it was a very smart way of like getting the model started, right? And then getting that kind of knowledge in of these dense features. Can you talk to us a bit about like that trajectory and like when did you decide to actually jam it in there for the stage one?
Yeah. So first thing first, as you noticed, Yasin, the model, I mean, the paper title was AMWE, and then it changed to Siglino. And the reason we changed is because we added like dance variants, which is, I can tell you a side story here, which is like kind of be funny. So when we started this project, like summer, we were not really confident about like early fusion that it's gonna work. Like just mixing image and text tokens and what's not. So we spent a lot of time. This model, up until maybe 75% of the duration of the project, was an MW. Like talking about both distillation and the perception model. And then we have like a perception model like trained actually up until convergence as an MW. And the reason we were doing this was we wanted to do like an MW because it just makes sense. because if you're doing early fusion, you want like experts, and then each modality can like take a set of experts. You can even like hard route like image and text tokens like throughout the experts, which means you go from depth like image and then text to like width. You just do them in width, right? So distillation in the beginning was done as an MOE. That was the first reason. The second reason we wanted to do an MOE because we wanted to do like multi-teacher distillation. And in multi-teacher, we wanted like kind of two models, which are not really having kind of the same semantics. So you want like Dino v3, which is very good at like what you call like local features, which are great for segmentation. But you do also want image representations which are aligned with text concepts, which means you need a model which is trained on captioning or like contrastive, which is the case of Siglip. And we wanted like kind of this like image text alignment plus like local features, which means we were forced to have like two teachers. And our assumption was like you do an MOE because each teacher now can like can occupy a certain number of experts, and then we can have like both like I would say like both capabilities together. So we do this training with all the tricks that you can see there in the paper. Like we train like natively at like native resolution. We mix all the stuff. We like all the stuff we have done in the paper. So that was actually the majority of the work in the project, and we spent a lot of time making sure this MOE is stable, because training MOEs, especially at small scale, is not easy. Like like load balancing, all these issues. We had like all kind of issues with these MOEs. And then before CVPR like reviews came out, I asked, like, I was an intern Sofian doing this. I asked him like, look, we should prepare like few small dense models, but you also should prepare like an ultra sparse MOE, which is like small. Like our MOE was, we had like two variants, like 1B, 2B, 1B active, 2B total, 1.3, 0.6. So we wanted even a smaller one. So we started like doing dense like for distillation for like 600 million, 300 million, and we started doing like ultra sparse MOEs, like very small ones, like 300 million and 80 million active. And the reason we were doing this was two reasons. First one is we wanted to be ready for the rebuttal, because I was kind of suspecting reviewers to ask why, because we in the paper of distillation we also like propose other stuff, not only the architecture, like the loss functions, the data, the way, and what's not. I was expecting the reviewers to say, okay, why don't you apply the same recipe over a dense variant? So like we are, let's say, in December, and we have all these models now. So I discussed with Phúc. We wanted to train now the bigger perception model. MOE is trained. We have this model already. And now we wanted to train a smaller variant of the MOE. Sorry, of the perception, right? And obviously, if you want to do the smaller variant, we had like very small, let's say, dense models, right? And we had also very small MOE models. So we discussed, we wanted to do like this idea of what you call like like MOE, but we have like hard routing of image and text tokens. You choose which experts are for the image and which experts are for the text. So we discuss and we say, okay, that was a Friday, I remember. We say, okay, let's do the small dense model, because yeah, we want to do small dense model, right? In one direction for the image, but we have the issue with the small model is the dense model is you have to replicate it for the for the text tokens, right? You cannot say I'm gonna use 28 experts for image and 4 experts for text. You have to have symmetry on the architecture, which means we are now back to a larger model. Okay, screw it. We're gonna do something very simple. We're just gonna train the dance as it is. Just train it dance. Like, we don't care. No modality specific. No MOE. Nothing. We have dance models. Just let's plug them. That was a weekend, I remember. So we plugged the 300 million. Okay. So we plugged the 300 million model on a Friday to do detection only. And then Monday morning, so we have like around 40K steps, which was our duration for sweeps. Monday we check the results, and then we see the loss functions are pretty much like very close. I was like, this is not possible. And we go there and test the model, and like test all the models and what's not, and do the benchmarking. And it turns out actually you don't need MOE, you don't need this like hard routing, none of that. Just dense works. Like
Crazy.
all our assumption that actually early fusion you cannot mix text with the image tokens and this kind of stuff was all wrong. So we had to essentially throw all the trainings we have done for MOEs. We had to change the title of the paper to Siglino because now we have dense models, and then the perception, like now our model is dense, which is better for us because dense we don't need like gem, which means our model can work on any GPU, can work on RTX, can work on A100.
Wow.
We don't need H100 for this model anymore. So this is how we ended up having perception as a dense model.
This is absolutely crazy, man. Thank you for sharing. This is fantastic, and I don't know, like it's so cool that like discovery like this happens because like you have some prior and then you go and then you do the things like with like your ideas, but then the actual result like come back and then you get the not a reality check, but just like you get like kind of a glimpse of the truth, right? Of what is actually better for the model to learn. It's amazing that you guys came up to that conclusion right in time. Oh, this is great.
That was like, and then we had to do okay. And then after this, what was the other question? Because as you know, we were training perception and OCR. So we were saying, okay, maybe it worked for perception because you don't actually need a lot of text generation. All you need is coord size sec. So maybe language is not required here that much as we think. Okay, maybe that's why dense works. And then we go, okay, let's try actually to train a 300 million OCR model, like the same thing, which is actually where you need to generate a lot of language, right? So you need maybe equal amount of modeling both for images and for language, for text. And then we train the OCR model, same thing, works, and like works just fine. So which is a bit more surprising than it works for perception actually, by the way. So
Oh, this is beautiful, man. This is so cool. Great. I have like two more questions. Well, first, like I want to know, like actually, I have two more questions. What's your next plan for this? I know you're talking about the second iteration of Falcon Perception. Do you have an idea about like what core things you want to mix in here, or like which direction you wanna take this model?
yeah, so essentially like V1, it was more or less to try out whether natively multimodal works from scratch, like we mix everything, and it works in an early fusion manner, and it works in an autoregressive way as well. And all of these three things were like were met over one capability, which is open vocab, referring expression, segmentation. So now we want to take it a bit further we want to build a perception engine, where this perception engine, it should be called by like larger models, and it has to be fast and reliable to the point where the same tasks, it does not make any sense to do it as part of the big model anyways. So we want to go for more grounded captioning, like captioning where we know where each object that the model mentions is in the image. And also we want to go agentic, which means our V2 has to be able to do like cropping, zooming, all the operations needed to solve the task if needed. And obviously reasoning, like it has to reason, like for example the ideas you just mentioned, like like refining the coord, like having multiple trials and what's not. So V2 gonna be slightly bigger in size, and we're gonna expand the territory or the the set of capabilities as much as we can, focusing on spatial intelligence. We won't be doing any math or any of that.
Right,
So it will be mostly like spatial intelligence, and we want to push it as much as we can, and till the boundary of where we can't do this anymore and we have to call for the orchestrator, like the bigger models, like where we're gonna work under them. For example, stuff requiring like a lot of knowledge, reading documents, like doing web search and what's not. So this is our direction, and this is what we are building.
Cool. This is really nice. And like When do you think it will be a good time to start to scale the model, up, given is like enough compute and given enough data? Do you want to still kind of stay within like a reasonable sub 1 billion token space and then like improve the architecture and then you scale? What's your take on that?
We don't have like I don't really have the answer now because it does depend on multiple factors. So the first factor is inference and efficiency because we still want to be like fast, reasonably fast, I would say.
Yeah.
So there will be like a ceiling, like decided just upon this constraint. And the second one is obviously the performance we want and how much to model. Usually start like small and we increase the size only when we see the model is not able to like absorb the information from the data like anymore. So yeah, we'll see.
Cool. Cool. Pretty nice. Okay, last question before we close this. Which AI research finding or area that may not be included in the model yet are catching your attention at the moment? Maybe Yasser and Phúc. Any finding in particular that you got very interested, even if there's no implementation that are pragmatic?
Yeah, I one of the things I really want us to explore is visual COT, which is something we see with the recent Meta Muse Spark. Like we draw on the image and what's not, and like look there and do things. We don't really see like the extent to which it could be like beneficial. It's not really well studied for now, but I think it's gonna be maybe an important block of what comes next for the large models. So I think like people have explored a lot of like the chain of thought, like the R1 style, like reasoning in the text token. What about like reasoning in the visual space? So this is something like that actually catches my interest, and want to look into it like next.
Cool, cool. And Phúc, what's your what got your interest?
For me, also slightly related to this about visual reasoning, but I'm thinking about visual generation as well.
Okay.
Like, can we also fold in the generation part as one big model? No more decoder, no more quantization. Everything, it's just a lie head, like our segmentation head, and with that, everything, generation capability, visual reasoning, they can happen in the same representation space. So
Right.
that might probably a bit far for us to do at the moment, but that is something, a general direction I think would be very interesting.
And is there any architecture or paper that are going this direction right now, or not even?
There is a few, but I don't think anything that's really meaningful, like unified.
Right.
Yes.
Cool. Well, guys, thank you very much. That was absolutely awesome. I know it's very late for you, so very big thank you to stay so late to answer all of my questions. It was a lot of fun. And yeah, do keep us updated with like the next iteration. I can see from like how you're describing the model that like you're just scratching the surface, and like I think you're really onto something. So I wish you the best. And if you need any help with augmenting the benchmark like labeling, I'm available. There's no need. There's no don't worry about it.
We will keep you accountable for this. Thank you for the outcome.
I might do a whole stream just like labeling your stuff, guys. Fantastic. Thank you. See you guys.
Thanks a lot, Yasin. I
Okay.
appreciate
Thank
it.
you.
Our pleasure.
Thank you a lot.
I'll wait you.
It was neat.
Have a nice day.
You too. And that was it for Falcon Perception. Again, I absolutely love when you get a sneak peek about like how actually the last run is done. I think it was something that like Lucas from RC said on Tuesday, that constraint really do help with research. Like when like I don't know, like you have constraint in budget, in compute, or in time, you start to kind of do these moves that are more pragmatic, but that are may get like some very surprising result. But you know that you can't just like meander around and just like look at everything. You have to make decision, right? And again, this model is a good example of that. So was absolutely awesome. I'm very excited to see where these guys are gonna like be able to pop up next, especially on the RL side. I think it was Vic from Moondream that explained how he was building the model, and it was a lot of reinforcement learning that was added, actually a lot of post training. So I think like if this model also go and follow a similar trajectory, we might get something cool. The level 2 issue is also very fascinating, that like it's able to kind of locate where everything is, right, and like count and stuff, but it's not. It has a hard time like doing the reading, as almost as like they are literate, but they are a lazy reader in some shape or form, right? A bit like I don't know, a toddler. You will ask this for a toddler, and then it will look, and like if they don't know how to read, you say like, hey, like pinpoint me the car with the Jaguar, and then I don't know, this other thing, and they'd be like, I have no clue what you're saying, and then they kind of randomly guess. But if you talk to that, say to them pinpoint me the car that is behind the first one, they be able to do it without any problem, because like they understand how the world works, right? So maybe this model just don't like really like to read. So that's also very interesting. Anyway, check out the paper, right? Falcon Perception. It's like 47 pages, but like really well written, and then you get like this whole story behind. There's also the other two paper, the PBench, right? Very interesting. And then there's the Siglino paper about the distillation that they've done. That you should check it out. So that is it. It was awesome, and we'll see each other next week. See you guys.